In this video, I'm going to give a brief overview of the Hessian-Free optimizer that can be used to train recurrent neural networks very effectively. This is a very complicated optimizer, and I don't expect you to get all the details of it from this video. I just want you to have a general feel for how it works, and then in the next video, we'll see how well it does on an interesting problem. When we're training the weights of a neural network, we're trying to get as far down the error surface as possible. So one question is, if we choose a given direction to go in, how much reduction in the error can we achieve by going just the right distance in that direction? How much does the error decrease before it starts rising again? And here we'll assume that the curvature is constant, i.e. we'll assume it really is a quadratic error surface. We're going to assume that the magnitude of the gradient decreases as we move down the gradient. That amounts to assuming that the error surface is concave upward like a bowl. The maximum reduction that we can get in the error by going in a particular direction depends on the ratio of the gradient to the curvature. So we want to move in directions that have a good ratio. Even if the gradient is quite small, we want the curvature to be even smaller. So here's an example of a direction we could move in, where the vertical axis corresponds to the error, the horizontal axis corresponds to the weights in the direction we're moving in, and the blue arrow corresponds to the reduction we get if we start at that red point. Here's a surface that has a gentler gradient, but because it's got a better ratio of the gradient to the curvature, we get a bigger reduction in the error by the time we get to the minimum. The question is, how can we find directions like that second one? Directions in which, even though the gradient may be small, the curvature is even smaller. So let's start with Newton's method. Newton's method addresses the basic problem with steepest descent, which is that the gradient isn't the direction you really want to go in. If the error surface has circular cross-sections, and it's quadratic, the gradient is a good direction to go in. It'll point straight at the minimum. So the idea of Newton's method is to apply a linear transformation that turns ellipses into circles. If we apply that transformation to the gradient vector, it will be as if we were going downhill in a circular error surface. To do this, we need to multiply the gradient dE by dW by the inverse of the curvature matrix. So H is the curvature matrix, sometimes called the Hessian. It's a function of the weights we have, and we need to take its inverse and multiply the gradient by that. Then we need to go some distance in that direction. If it's a truly quadratic surface, and we choose epsilon correctly, which is quite easy to do, we'll arrive at the minimum of the surface in a single step. Of course, that single step involves something complicated, which was inverting that Hessian matrix. The problem with this is that even if we only have 1,000,000 weights in our neural network, the curvature matrix, the Hessian, will have 1,000,000,000,000 terms. It's completely infeasible to invert it. So curvature matrices look like this. For each weight, Wi or Wj, they tell you how the gradient in one direction changes as you change in another direction. In other words, as I change weight I, how does the gradient of the error with respect to weight j change? That's what a typical off-diagonal term tells you. The terms on the diagonal tell you how the gradient of the error changes in the direction of a weight as you change that weight. So the off-diagonal terms in a curvature matrix correspond to twists in the error surface. A twist means when you travel in one direction, the gradient in another direction changes. If we have a nice circular bowl, all those off-diagonal terms are zero. As we travel in one direction, the gradient in other directions doesn't change. So what's going wrong with steepest descent when you have an elliptical error surface is that as we travel in one direction, the gradient in another direction changes. And so if I update one of the weights at the same time as I'm updating all the other weights, all those other updates will cause a change in the gradient for the first weight. And that means when I update it, I may actually make things worse. The gradient may have actually reversed sign due to the changes in all the other weights. And so as we get more and more weights, we need to be more and more cautious about changing each one of them, because the simultaneous changes in all the other weights can change the gradient of a weight. The curvature matrix determines the size of those interactions. So we have to deal with the curvature. We can't just ignore it. And we'd like to deal with it without actually inverting a huge matrix, because the matrix has too many terms in a big neural net. One thing we can do is to just look at the leading diagonal of the curvature matrix and make our step size depend on that leading diagonal. That helps a bit. It will get us to make different step sizes for different weights. But the diagonal terms only a tiny fraction of the interactions. So we're ignoring most of the terms in the curvature matrix when we do that. In fact, we're ignoring nearly all of them. Another thing we could do is try and approximate the curvature matrix with a matrix of much lower rank that captures the main aspects of the curvature matrix. That's what's done in Hessian-Free methods and LBFGS and many other methods that try and do an approximate second order method for minimizing the error. In the Hessian-Free method, we make an approximation to the curvature matrix, and then we assume that the approximation is correct. So we assume we know what the curvature is, and that the error surface really is quadratic. And then, starting from wherever we are now, we minimize the error using an efficient technique called conjugate gradient. Once we've done that, once we've got close to a minimum on this approximation to the curvature, we then make another approximation to the curvature matrix, and we use conjugate gradient to minimize again. It's also important in recurrent neural networks to add a penalty for changing any of the hidden activities too much. That will prevent us, for example, from changing a weight early on that causes huge effects later on in a sequence. We don't want to get effects that are too big, and if we look at the changes in the hidden activities, we can prevent that by penalizing those changes. If we put a quadratic penalty on those changes, we can combine that with the rest of the Hessian-Free method. The last thing I need to explain is conjugate gradient, and I'm just going to explain that briefly. Conjugate gradient is a very clever method that, instead of trying to go straight to the minimum, like in Newton's method, tries to minimize in one direction at a time. So it starts off by taking the direction of steepest descent, and goes to the minimum in that direction. That might involve re-evaluating the gradient, or re-evaluating the error a few times, to find the minimum in that direction. Once it's done that, it now finds another direction and goes to the minimum in that second direction. The clever thing about the technique is it chooses its second direction in such a way that it doesn't mess up the minimization it already did in the first direction. That's called a conjugate direction. Conjugate means that as you go in the new direction, you don't change the gradients in the previous directions. It's a funny idea. It's like the idea of a twist in an error surface. A twist means when you go in one direction, you change the gradient in another direction. And a conjugate direction is one you can go in that in a sense doesn't have a twist. You go in that direction, and the gradient in the first direction doesn't change. So here's a picture of an ellipse, and the red line is the major axis of the ellipse. We start off by doing one step of steepest descent all the way to the minimum in that direction. And if you think about it a bit, you can see that the minimum won't actually lie on the red line. On the red line, the gradient will be 0 at right angles to that red line, because it's the bottom of the ravine. but the direction we're going in isn't actually at right angles to that line. We can make a little bit more progress by making a small step at right angles to the red line and then a small step along the red line. Since the red line slopes down towards the middle of the ellipse, that's going to make some progress for us. So when we minimize in the first direction, we'll go slightly across the bottom of the ellipse. And when we reach that point that's a minimum, there's an interesting property of all the points that lie on the green line. On that green line, the gradient in the direction of that black arrow is 0. So we can go anywhere along that green line and we won't destroy the fact that we're at a minimum in the direction of the black arrow. If we can keep doing that for many directions in a high-dimensional error surface, we'll eventually be at a minimum in many different directions. And if we're at a minimum in as many different directions as there are dimensions in the space, we'll be at the global minimum. So, we take this first step of steepest descent, we then figure out, and I'm not going to explain how we do that, we figure out the direction of that green line, and then we do a search along the green line to find how far we should go in order to minimize the error along the green line, and we take our second step, like this. And now in this two-dimensional space, we'll be at the minimum, because we're at the minimum in the direction of the first step, and we're now at a minimum in the direction of the second step, while still being at a minimum in the direction of the first step, and so that must be the global minimum. What conjugate gradient achieves is that it gets to the global minimum of an n-dimensional quadratic surface in only n steps. It's very efficient. It does that because it manages to get the gradient to be 0 in n different directions. They're not orthogonal directions, but they are independent of one another, and so that's sufficient to be at the global minimum. More importantly, in many less than n steps on a typical quadratic surface, it will have reduced the error very close to the minimum value. And that's why we use it. We're not going to do the full n steps. That would be as expensive as inverting the whole matrix. We're going to do many less than n steps, and we're going to get quite close to the minimum. You can apply conjugate gradient directly to a non-quadratic error surface, like the error surface for a multi-layer nonlinear neural net, and it usually works quite well. It's essentially a batch method, but you can apply it to large mini-batches, and when you do that, you do many steps of conjugate gradient on the same large mini-batch, and then you move on to the next large mini-batch. That's called nonlinear conjugate gradient. The Hessian-Free optimizer uses conjugate gradient for minimization on a genuinely quadratic surface, and that's what conjugate gradient is best at. It works much better for that than for a nonlinear surface. This genuinely quadratic surface that HF is using it for is the quadratic approximation to the true surface that was made by the Hessian-Free method. So it makes that approximation. It uses conjugate gradient to get close to a minimum for the first approximation, and then it makes a new approximation to the curvature and does it again. We're now going to apply Hessian-Free optimization to the task of modelling character strings from Wikipedia. So the idea is you read a lot of Wikipedia and then try to predict the next character. Before we get to see what the model learns, I want to describe why we need multiplicative connections and how we can implement those multiplicative connections efficiently in a recurrent neural network. I need to start by explaining why we chose to model character strings rather than strings of words, which is what you normally do when you're trying to model language. The web is composed of character strings. Any learning method that's powerful enough to understand what's going on in the world by reading the web ought to find it trivial to learn which strings make words. As we'll see, this turns out to be true. So we're going to be very ambitious here. We want something that will read Wikipedia and understand the world. If we have to pre-process the text in Wikipedia into words, it's going to be a big hassle. There's all sorts of problems. The first problem is morphemes. The smallest units of meaning, according to linguists, are morphemes. So we're going to have to break up a word into these morphemes if we want to deal with it sensibly. The problem is, it's not quite clear what morphemes are. There's things that are a bit like morphemes, but that a linguist wouldn't call a morpheme. So in English, if you take any word that starts with the letters SN, it has a very high chance of meaning something to do with the lips or nose, particularly the upper lip or nose. So words like snarl and sneeze and snot and snog and snort, there's too many of these words for it just to be coincidence. Many people say, yes, but what about snow? That's got nothing to do with the upper lips or nose. But ask yourself, why is snow such a good word for cocaine? Then there's words that come in several pieces. So normally we'd want to treat New York as one lexical item. But if we're talking about the New York Minster roof, then we might want to treat New and York as two separate lexical items. And then there's languages like Finnish. Finnish is an agglutinative language, so it puts together lots of morphemes to make great big words. So here's an example of a word in Finnish that takes about 5 words in English to say the same thing. I have no idea what this word means, but despite my lack of understanding, it makes the point. So here's an obvious kind of recurrent net we might use to try and model character strings. It has a hidden state, and in this case we're going to use 1500 hidden units, and the hidden state dynamics is that the hidden state at time t provides inputs to determine the hidden state at time t plus 1, and the character also provides some inputs. So we add together the effect of the current character with the previous hidden state to get the new hidden state. And then when we arrive at a new hidden state, we try and predict the next character. So we have a single softmax over the 86 characters, and we get the hidden state to try and assign high probability to the correct next character and low probability to the others. And we train the whole system by back-propagating from that softmax the log probability of getting the correct character. We back-propagate that through the hidden to output connections, back through the hidden to character connections, and then back through the hidden to hidden connections, and so on all the way back till the beginning of the string. It's a lot easier to predict 86 characters than 100,000 words, so it's easy to use a softmax at the output. We don't have the problem of a great big softmax. Now I want to explain why we didn't use that kind of recurrent net, but instead used a different kind of net that worked quite a lot better. You could arrange all possible character strings into a tree with a branching ratio of 86 in our case, and what I'm showing here is a tiny little subtree of that great big tree. In fact, this little subtree will occur many times, but with different things that are represented by that ... before the fix. So this represents that we had a whole bunch of characters, then we had F, and then I, and then X. And now if we get an I, we're going to go to the left. If we get an E, we're going to go to the right, and so on. So each time we get a character, we move one step down in this tree to a new node. There's exponentially many nodes in the tree of all character strings of length n. So this is going to be a very big tree. We couldn't possibly store it all. If we could store it all, what we'd like to do is put a probability on each of those arrows. And that will be the probability of producing that letter given the context of the node. In an RNN, we try and deal with the fact that the full tree is enormous by using a hidden state vector to represent each of these nodes. So now what the next character has to do is take the hidden state vector that's representing a whole string of characters followed by fix and operate on that hidden state vector to produce the appropriate new hidden state vector if the next character was an I. So when you see an I, you want to turn the hidden state vector into a new hidden state vector. A nice thing about implementing these nodes in this character tree by using the hidden state of a recurrent neural network is that we can share a lot of structure. For example, by the time we arrive at that node that says fix, we may have decided it's probably a verb. And if it's a verb, then I is quite likely because of the ending ing, and that knowledge that I is quite likely with a verb can be shared with lots of other nodes that don't have fix in. So we can get I to operate on the part of the state that represents that it's a verb, and that can be shared between all the verbs. Notice that it's really the conjunction of the current state we're at and the character that determines where we want to go. We don't want I to give us a state that's expecting to get an n next if it wasn't a verb. So we don't want to say that I tends to make you expect an n next. We really want to say, if you already think it's a verb, then when you see an I, you should expect an n next. It's the conjunction of the fact that we think it's a verb and that we saw an I that gets us into this state labelled fixi that's expecting to see an n. So we're going to try and capture that by using multiplicative connections. Instead of using the character inputs to the recurrent net to give extra additive input to the hidden units, we're going to use those characters to swap in a whole hidden to hidden weight matrix. The character is going to determine the transition matrix. Now if we did that in the naive way, we'd have each of the 86 characters define a 1500 by 1500 matrix, and that would be a lot of parameters. If we have that many parameters, the net's likely to overfit unless we run it on a huge amount of text for which we might not have time. So the question is, can we achieve this kind of multiplicative interaction where the character determines the hidden to hidden weight matrix using many fewer parameters by making use of the fact that characters have things in common? For example, all of the digits are all quite similar to each other in the way in which they make the hidden state evolve. So we want to have a different transition matrix for each of those 86 characters, but we want those 86 character-specific weight matrices to share parameters. And that's a reasonable thing to do because we know that characters 8 and 9 should have very similar transition matrices. So here's how we're going to do it. We're going to have things called factors, and they're going to be denoted by this little triangle with an F above it. What that factor means is that Group A and Group B interact multiplicatively to provide input to Group C. So what each factor does is it first computes a weighted sum for each of its two input groups. So we take the vector state of Group A, which I'll just call A, and we multiply that by the weights on the connections coming into the factor. In other words, we take the scalar product of the vector A and the weight vector U, and that gives us a number at the left-hand vertex of that triangle. Similarly, we take the vector state of Group B and we multiply it by the weight vector W, and we get another number at the bottom vertex of the triangle. We now multiply those two numbers together, and that gives us a number, a scalar, and we use that scalar to scale the outgoing weights V in order to provide input for Group C. So the input to Group C is just the product of the two numbers that come into the two vertices of the triangle times the outgoing weight vector V. We can write that as an equation. The input that factor F provides to Group C, so it's vector input to Group C, is a scalar input to f from group B that's got by multiplying the state of group B by the weights W, f, times a scalar input to f from group A that's got by multiplying the state of group A by the weights U. We then take the product of those two scalars and multiply the weight vector Vf by that, and that's the input that the factor gives to group C. Then, of course, we're going to have a whole bunch of those factors. There's another way we can think about these factors that gives more insight into what's going on. Each of the factors actually defines a very simple kind of transition matrix. It's a transition matrix that has rank 1. So the equation we had on the previous slide treats a factor as computing two scalar products, multiplying them together, and then using that as a weight on the outgoing vector v. We can rearrange that equation so that we get one scalar product, and then we've rearranged the last bit so that now we take the outer product of the weight vector u and the weight vector v, and that gives us a matrix, and the scalar product that we computed by multiplying b by w is just a coefficient on that matrix. So we get a scalar coefficient, we multiply a rank 1 matrix by that scalar coefficient to give us a scaled matrix, and then we multiply the current hidden state A by this matrix to determine the input that factor f gives to the next hidden state. If we sum that up over all the factors, the total input to group C is just a sum over all factors of a scalar times a rank 1 matrix, and that sum is a great big matrix. That's the transition matrix, and it gets multiplied by the current hidden state to produce the new hidden state. So we can see that we've synthesized a transition matrix out of these rank 1 matrices provided by each factor, and what the current character in group B has done is it's determined the weight on each of these rank 1 matrices. So B times W determines a scalar weight, a scalar coefficient, to put on each of the matrices out of which we're going to compose this great big character-specific weight matrix. So here's a picture of the whole system. We have a number of factors. In fact, we'll have about 1,500 factors. And the character input is different in that only one of those is active. So there'll only be one relevant weight at a time. And that weight from the current character k, which is called WKF, is the gain that's used on the rank 1 matrix got by taking the outer product of u and v. So the character determines a gain, WKF. You multiply the rank 1 matrix uv by that gain. You add together those scaled matrices for all the different factors, and that's your transition matrix. In this video, we're going to see what happens when the Hessian-Free optimizer is used to optimize a recurrent neural network containing multiplicative connections, and the network is trained to predict the next character in Wikipedia. The network is trained on millions of characters, and it works remarkably well. It learns a lot about English, and it becomes very good at completing sentences in interesting ways. Ilya Skiva used 5 million strings of 100 characters each, taken from English Wikipedia. For each string, he starts predicting after 11 characters. So the recurrent network starts off in a default state. It reads 11 characters, changing its hidden state each time, and then it's ready to start predicting, and it gets trained by backpropagating the errors it makes in prediction. He used the Hessian-Free optimizer, and it took about a month on a very fast GPU board to get a really good model. His current best recurrent neural network for character prediction is probably the best single model there is for predicting characters. You can do better than this model by combining many different models using a neural network to decide which one to use. But for a single model, Ilya's is as good as it gets. It works in a very different way from the best other models. So Ilya's model can balance quotes and brackets over long distances. Any model that relies on matching a specific previous context can't do that. So, for example, if it has a bracket and it wants to close it 35 characters later, in order to do that properly, a model that relies on matching previous contexts would have to match all 35 intervening characters, and it's very unlikely that it has that whole string stored. Once the model's learned, you can see what it knows by generating strings from the model. Of course, you have to be very careful not to overinterpret what it says. The way we generate strings is we start in the default hidden state. We then give it a burn-in sequence, so we feed it characters and let it update its hidden state after each character. And then we let it start predicting. We look at the probability distribution it predicts for the next character. We pick a character randomly from that distribution. So if it predicts that the probability of a Q is 1 in 1,000, we pick Q 1 time in 1,000. We then tell the net that whatever character we picked was the character that actually occurred, and ask it to predict the next character. In other words, we're telling it that whatever it guesses is correct. We let it continue to pick characters until we've got as many as we want, and then we look at the strings it produces to see what it knows. So here's an example of a string produced by Ilya's network after some burn-in. This was selected from a much longer passage of text, but it's a continuous passage, which shows you that it works pretty well. You'll notice that it has weird semantic associations. So Opus Paul at Rome. No person would ever say that, but we understand that Opus and Paul and Rome are all highly interconnected. You'll notice it doesn't really have any long-range thematic structure. It pretty much changes topic after each full stop. One amazing thing is that it produces very few non-words. What that means is that even though it's predicting probabilities of characters, as soon as you've got enough characters so there's only one way to complete it as an English word, it will predict the next character almost perfectly. If that wasn't the case, it would produce non-words. Even when it does produce a non-word, like the word in red, it's a very good non-word. I'm not absolutely certain, or I wasn't when I first saw it, that ephemerable wasn't an English word. You'll also notice it's produced a closing bracket without an opening one. So it doesn't always balance brackets, it just does it quite frequently. You'll also notice at the end that it's produced an opening quote and then a closing quote much later. That's consistent behaviour on its part. It really did produce that closing quote because it had an open quote earlier on. If you look at this text, you can see there's a lot of good local syntax. So little strings of 3 or 4 words look perfectly reasonable. There's also lots of semantic knowledge. So one thing we could do is we could test the model by giving it carefully designed strings to see what it knows. So I tried giving it a non-word. The word thrunge, T-H-R-U-N-G-E, is not an English word, but most English speakers, when they see that word, would expect it to be a verb because of its form. So I gave it opening contexts in which that might be a verb to see what character was most likely to come next. So if you give it Sheila Thrunge and ask for the next character, the most frequent one is an S, which suggests that it knows that Sheila is singular, just from reading Wikipedia. If you give it People Thrunge, the most frequent next character is a space, not an S, which suggests that it knows that people is plural. I then tried giving it a list of names. So I used capitals for the names with a comma in between, and I put a capital T for Thrunge so it looked like a name to see what it would do with that. So it actually completed it as a name, and if you look at the name it made, it's not a bad name. It indicates that it knows an awful lot about names in many languages. You can also give it the meaning of life is and see what comes next. If it produced 42, that wouldn't be very interesting, because I'm fairly sure that'll be somewhere in Wikipedia. It produces random things, but in its first 10 tries, it produced the meaning of life is literary recognition, which is syntactically and semantically sensible. We then trained the model some more and presented it with the meaning of life is again. We took the first 10 things it produced, and I'm going to show you the most interesting one. The completion it produced for the meaning of life is suggests that by reading Wikipedia, it really is beginning to understand something about the meaning of life. That's probably just wild overinterpretation, though. So here's its completion. So what does the model know after it's read all these characters of Wikipedia? Well, it certainly knows about words. It produces almost always English words. It will produce strings of initials, typically in capitals. It can produce numbers and dates and things like that. But it doesn't produce non-words very often. It produces them extremely rarely, and when it does produce them, they're typically very plausible non-words. It also knows a lot about proper names, like Thrungelini del Rey. It knows about dates and numbers, and the context in which they occur. It's good at balancing quotes and brackets, and in fact it can actually count brackets. If you give it no opening brackets, it's very unlikely to produce a closing bracket. If you give it one opening bracket, it's quite likely to produce a closing bracket in the next 20 characters or so. If you give it two opening brackets, it'll produce a closing bracket very quickly. Giving it 3 doesn't seem to make it any faster. It clearly knows a lot about syntax because it's able to produce these little strings of English words that are sensible. But it's very hard to pin down exactly what form this knowledge has. It's not like trigram models, which have just learned little sequences of words, or rather they have a table that contains little sequences of words. It's actually synthesizing strings of words, and it's synthesizing them with sensible syntax. It's very hard to say, though, what form that syntactic knowledge has. It's not a bunch of rules like a linguist has. It's much more like what's in the linguist's head when he speaks his native language. It knows a lot of weak semantic associations. So, for example, it only ever produced the word Wittgenstein once, and it produced that soon after producing the word Plato. So it knows that Plato and Wittgenstein are associated. Well, that's a pretty good assumption. It clearly knows that cabbage is associated with vegetable. It doesn't know much about the precise ways in which these things are associated. People are like that too, if you get them to respond very fast. So I'm going to ask you a question, and I want you to shout out the answer. So you're sitting there watching this video, and this experiment will work by far the best if you actually shout out the answer out loud. And you have to shout it out really fast. You get rewarded for responding very quickly. It doesn't matter what you say, you just have to respond fast. So the question is, what do cows drink? Most people, when given that question, shout out milk. Now, most cows don't drink milk most of the time. We say milk because it's associated with both drink and with cow, but it's not logical to say milk. Recently, Thomas Mikolov and his collaborators have been training large recurrent neural networks to predict the next word in large datasets. They use the same technique as the feed-forward neural nets, that first convert a word to a real-valued feature vector, and then use those feature vectors as input to the rest of the network. and they do better than the feed-forward neural nets. They also do better than the best other models, and when you average them with the best other models, they do better still. So that's the best language models there are currently. One interesting property of the RNNs is that they require less training data than the other methods to reach a given level of performance. More importantly, as the data sets get bigger, the RNNs improve faster than the other methods. So methods like trigrams, for example, do get better with bigger datasets, but it's a very slow process. You need to double the size of the dataset to get a small improvement. With RNNs, they can make much better use of the data. This means it's going to be very hard to beat them as datasets get bigger. I think it may be the same story as for object recognition with large deep neural nets, that once the neural nets get ahead, they can make better use of faster computers and bigger datasets, and so it's going to be very hard for other methods to catch up. In this video, I'm going to describe echo-state networks. These use a clever trick to make it much easier to learn a recurrent neural network. They initialize the connections in the recurrent neural network in such a way that it has a big reservoir of coupled oscillators. So if you provide input to it, it converts that input into the states of these oscillators, and then you can predict the output you want from the states of these oscillators, and the only thing you have to learn is how to couple the output to the oscillators. This entirely gets rid of the problem of learning hidden-to-hidden connections, or even input-to-hidden connections. However, to get these networks to be good at complicated tasks, you need a very big hidden state. As we'll see at the end of the video, there's no reason not to use the initialization that was carefully designed for echo-state networks, and then to use backpropagation through time with momentum to train the networks to be even better at the tasks that they're doing. One interesting and quite recent idea about training recurrent neural networks is to not train the hidden-to-hidden connections at all, but to just fix them randomly and hope that you can learn sequences by just training the way they affect the outputs. This has strong similarities with old ideas about perceptrons. So a very simple way to train a feed-forward neural network is to make the early layers of feature detectors just be random. You put in sensible-sized random weights, and then all you learn is the last layer, so that you're learning a linear model from the activities of the hidden units in the last layer to the outputs. And of course it's much faster to learn a linear model. This relies on the idea that a big random expansion of the input vector can often make it easy for a linear model to fit the data, when it couldn't fit the data well just looking at the raw inputs. So in the little neural network here, those red weights would be fixed at random. They would expand the input vector, and then using that expanded representation, we'd try and fit a linear model. This actually has some quite strong similarities with support vector machines, which are really just a really efficient way of doing this. So those same ideas, many years later, were recycled for recurrent neural networks. The idea is to make the input-to-hidden connections and the hidden-to-hidden connections have random values that are carefully chosen, and just learn the final layer of hidden-to-output connections. The learning is then very simple if you use linear output units, and it can be done extremely fast. This approach is only ever going to work if you set the random connections very carefully so that the recurrent neural network doesn't die out with no activity and doesn't explode. So the way they set the random connections in an echo-state network is they set the hidden-to-hidden weights so that the length of the activity vector stays about the same after each iteration. For those of you used to linear systems and matrices, you're setting it so the spectral radius is 1. that is, the biggest eigenvalue of the matrix of hidden to hidden weights is 1, or it would be 1 if it was a linear system. And you want to achieve the same property in a nonlinear system. If you set those weights to be about the right magnitude, then an input can echo around in the recurrent state for a long time. It's also important to use sparse connectivity. So instead of having lots of medium-sized weights, we have a few quite large weights, and nearly all the weights are 0 in the hidden-to-hidden connections. What this does is it makes a lot of loosely coupled oscillators. So information can hang around in one part of the net without being propagated to other parts of the net too quickly. It's also important to choose the scale of the input to hidden connections very carefully. Those connections need to drive the states of the loosely coupled oscillators, but they mustn't wipe out information that those oscillators contain about the recent history. Fortunately, the learning is very fast in echo state networks, so we can afford to experiment with the scales of the input to hidden connections. You could think of it as a little learning loop that's just learning the scales of those connections, and it's doing it by sort of feedback that involves the experimenter. It also helps to learn the level of sparseness that's needed in the hidden to hidden connections. And again, because the learning is so fast, you can afford to experiment with that. That's important because it's often necessary to do those experiments to get the system to work well. So I'm now going to show you a simple example taken from the web of an echo state network. It has an input sequence which is a real value that varies with time and specifies the frequency of a sine wave for the output of the echo state network. So you'd like this thing to generate sine waves, and the input is going to specify the frequency. The target output sequence is going to be a sine wave with the frequency specified by the input. And it's going to be learned simply by fitting a linear model that takes the states of the hidden units and from those tries to predict the correct scalar output value. So here's a picture taken from Wikipedia of an echo state network doing this problem. The input signal is the desired frequency of the sine wave. The output signal after it's learned, or the teacher signal when it's learning, is a sine wave with the frequency specified by the input. And the stuff in the middle is a big dynamical reservoir so that the inputs coming from the input signal drive those loosely coupled oscillators and cause complicated dynamics that goes on for a long time. And those output weights are learning to map that complicated dynamics to the particular dynamics you want for the output. All the other pictures are showing you the actual dynamics of individual units inside the dynamical reservoir. One thing to notice is that there are also connections from the output back to the reservoir. Those aren't always needed, but they help to tell the reservoir what output's been produced so far. So here's an example of what the system actually produces after it's learned, and you can see that at the beginning it's producing a sine wave in phase. At the end it's producing a sine wave of the right frequency, but the phase is wrong, and that's because we weren't telling it what phase the sine wave should be in. So it's satisfying the requirements of producing an appropriate frequency. There are some very good aspects of echo state networks. They can be trained very fast because they're just fitting a linear model. They also demonstrate how important it is to initialize the hidden to hidden weights sensibly. And they can do quite impressive modelling of one-dimensional time series. That's where they excel. They can look at a time series for a while and then predict it very well a long time into the future. What they're not so good at is modelling high-dimensional data, like frames of acoustic coefficients or frames of video. In order to model data like that, they need many more hidden units than a recurrent neural network where you train the hidden-to-hidden connections. Recently, Ilya Sutskever tried something which is fairly obvious, which is to initialize a recurrent neural network using all the tricks developed by the people doing echo state networks. Once you've done that, you know you could learn quite well just by learning the hidden-to-output connections. But then presumably you could learn even better if you also learned to make the hidden-to-hidden weights better. So Ilya tried using the echo state network initializations, but then training with backpropagation through time. He used RMS prop with momentum, and he discovered that that is actually a very effective way to train recurrent neural networks.